And start. Hello and welcome back to Calculus 3. We are continuing chapter 11. Hopefully today we get to those both sections done, 11.8 and 11.9. 11.8 is on length of curves, and you had your introductory lecture in Calculus 2. If you remember that formula, the length of curve with L equals square root 1 plus f prime squared dx. Yeah, dx.
You mean as an integral?
As an integral, yes. So we are going to build up this Calculus 2 formula, which you are supposed to know from Calc 2, right? So AB, integral a to b, square root of 1 plus f prime squared dx. Where is this formula coming from? If you have a curve and you want to calculate the length, let's say from A to B, you will partition this, and each one of these will be a small delta L. So now, when I zoom in, we get a curved little piece, delta L, with a straight line approximation. And now that straight line has delta x in length and delta y in height. That's the change of length and change of height. You write simple Pythagorean theorem. Delta L is equal to delta x squared plus delta y squared. Well, these are, let's put the parentheses. And we need a square root, right? Because delta L needs to be squared as well. We do not have to put plus minus because the lengths are always positive. So that's that. Delta L. So now we have we have the formula, and we know that this formula is for one small piece. What I want to do is I want to have a lot of these, right? So I can multiply this by delta x over delta x. So now we are doing mathematical gymnastics over here. We have our delta x squared plus delta y squared, and we multiply this by delta x over delta x. Now, the delta x on the bottom in denominator is going to undergo the square root, and in that process we'll pick up a square. So we have delta x squared over delta x squared plus delta y squared over delta x squared. And then on the outside you just have delta x left. Inside you will have 1 plus, you have delta y over delta x squared, delta y over delta x squared, delta x on the side, right? We know that delta x is the same as dx from chapter 5 in Calc 1. So all we need to do is to now say that length is going to be, if we are using the Riemann sum, this is one single little length. We know that we need to add infinitely many of those, and that will give us the integral from a to b. And then you just write 1 plus delta y over delta x. You write that as a derivative of a function. And then that's squared, because there is a square under the radical. And then instead of writing delta x, you put dx. This is a Calculus 2 derivation for length of curve. Length of curves in Cartesian coordinates. The XY version, right? And you had plenty of problems and practice in Calc 2. In Calculus 3, we are learning two new formulas. One is going to be expressed through the parametric equations, and the next one is the polar version of the same thing. So let's go into Calc 3 parametric version. To obtain parametric version, we are simply going to play with, again, we'll do some mathematical gymnastics. The honors section is going to be responsible for this derivation for the exam as one of the possible questions. So we start with a Calculus 2 formula, as is. And what we do is we multiply the equation by dt over dt, because we know that the parametric form is done in the terms of parameter t. So we are going to multiply by dt over dt, and then we are going to rearrange this as dx over dt times dt. And it's dx dt that gets multiplied under the radical. So what do we get? We get L, a to b. Inside the radical, I have old 1 plus f prime squared times dx dt squared. And then there is dt left on the outside. So you have your standard Calculus 2 formula in black. You are multiplying formula with red to convert it into parametric form because you need it to be dt. But then you rearrange the stuff in a blue bubble. Instead of having dx times dt over dt, you move the denominator dt under dx. So you have dx over dt times dt. You leave dt alone, right, which is this puppy here. You leave the dt alone and you multiply dx dt under the radical. So now we distribute under the radical 1 times dx dt squared is dx dt squared, and we write our derivative prime squared as dy dx squared times dx dt squared dt, where clearly dx squared and dx squared cancel, and we get our formula for length of curve in parametric form. It is simply dx dt squared plus dy dt squared dt. So this is your formula that you will use on the exam to calculate the length of the curve. So length of curve parametric form. What are you given in a parametric form? Well, you are given two parametric equations. You are given x is equal some function of t, and y is given some other function g of t. Well, you will find these derivatives, f prime and g prime, and you will just plug them in and integrate. It's a very simple set of steps to compute the formula. You just have to be careful of what kind of horror you are going to have to integrate, right? Which is where your use substitution and by parts and trig sub and partial fraction decomposition, right? Now we're going to try and keep this civil because, you know, there is no need for partial fraction embedded in trig sub, right? Kind of questions. We have software to deal with those situations. So to calculate length of curve, parametric form, how about we calculate the circumference of a circle, right? That should be civil enough. Circle is given as, let's say, radius 6. So 6 cosine t and 6 sine t on 0 to t to 2 pi for full circle. Well, I need dx dt, which is going to be negative 6 sine squared, sine t, and dy dt is going to be 6 cosine t. The length of curve will be 0 to 2 pi because those are the limits on t, and we have a square root of negative 6 sine t everything squared plus positive 6 cosine t everything squared dt. When we square everything, we get 36 sine squared t plus 36 cosine squared t dt. We can factor 36, take the square root of it, and kick it in front of the integral. What does it become? Factor 36, take the square root, and kick it in front of the integral. 6, very good. 6 integral 0 to 2 pi of the square root of sine squared t plus cosine squared t. How much is that? Thank you. It's a square root of 1, which is just 1. And I hope you see that the answer is 12 pi. Now, if you are to present this answer to an ancient Greek, you'll be dying laughing, because in ancient Greece, like 2,000 years ago and more, it was known that the circumference of the circle is 2 pi r. Your r is 6, so clearly 12 pi, without going any of these. But this could be, you know, this could come in handy You know, let's say someone asks you why. There you go. It's a conversation starter if you're on a date. You know, with a question, now what you like to do or your hobbies. You write this on a napkin. Right? So, good. So that would be length of curves using parametric form. Now we are going to jump into polar form for length of curves, and we're done. If you remember polar coordinates are listed as r theta. We will have the radius and angle to locate the point. Radius r and angle theta. What you also have at the same point is also xy. These two worlds are connected through conversion formulas. X equals r cosine theta and y equals r sine theta. So these two formulas are conversion factors between the two worlds. If you are having issues with this, go back to the first homework I posted, and then also go back to 10.2, and 10.3, and work on your polar coordinates. We are going to upgrade polar coordinates a lot in this course into 3D later. Obviously, stop by the office hours or stay after class if you have additional questions. So polar coordinates are coordinates for the 2D system, and the polar coordinates are complementing the xy coordinates. Xy coordinates are rectangular. They deal with sharp angles, you know, rectangles, squares, triangles, and things like that. Polar coordinates are dealing with rounded 2D objects like circles or ellipses or cardoids, which are, look at, cardoids look like a heart. They look like this. And then those flower pictures that you've seen and so on. So polar coordinates are good for that. And the xy coordinates are absolute disaster for things like this. And the vice versa. If you try to use polar coordinates on a rectangle, good luck. It's a living nightmare. All right? So each one of these coordinates is the king in its own domain, right? So polar coordinates are good for rounded shapes in 2D system. Now, when you have a polar coordinate, and you are talking about, again, circle, ellipse, or cardoid, or a flower, we would like to know the length of curve for those as well. We start with our Calculus 2 formula, AB of square root, thank you, of 1 plus f prime squared dx. You know what? It's f prime. It's dy dx squared. And then we have dx. We are going to use the conversion to replace all of the dy's and dx's with r and theta equivalents. Now, there are some subtleties here. You have to be very careful. When you are talking functions in polar coordinates, your r is f of theta. That means that every r you see is a function. So now, if I want to take derivatives of these puppies, because I need to be able to plug them in, I have to use chain rule and product rule, because r times cosine theta is a function times a function. Remember that r is a function, and sine theta is function as well. So you have function times function. That's a product rule. So these derivatives over here are not basic. We have to say that your dx d theta is going to be, and now you have the entire product rule to worry about. R is a function. So copy r, derivative of cosine is negative sine theta, plus copy the second, which is cosine theta, times r prime. This is the derivative if you are switching from x into the polar, right, with differentiation here. Now we have also dy d theta, which is going to be copy the first, derivative of the second, plus copy second, theta, times derivative of the first, r prime. Now, we don't like to write r prime. We're just going to put f of theta instead. So, I am going to clean this up. Dx d theta is going to be given, and I'm going to write the cosine term first, because I don't want negative to lead. So I have f prime of theta cosine theta minus f of theta sine theta. So I replaced my r's with f of theta, and then I also put the cosine term first because it was positive. Now, to keep consistent with f prime first, I'm also going to swap the terms from the bottom equation. So I'm going to leave with f prime theta sine theta plus f theta cosine theta. I hope that you see that if I divide these two equations, obviously divide y by x, I'm going to get formula for dy dx. dy dx is going to be f prime theta sine theta plus f of theta cosine theta divided by f prime theta cosine theta minus f of theta sine theta. Wow! We got our derivative dy dx. This entire derivation you see here is done in Calculus 2 in lecture 10.3, and it's part of your calculus textbook. You can go and verify this calculation. It's spelled out in the book. This is the way to find the derivative dy dx using the polar function input. Now, we see dy dx in your formula over here. You will multiply d theta over d theta, creating dx over d theta. There it is. Plug everything in, shovel through algebra, and at the end, you have the formula that we need for polar form. So now, we have the good old Calculus 2 length of curve dy dx squared dx. Again, red, we are multiplying by d theta over d theta. And as I did the bubble before, rewrite this as dx d theta times d theta, where the dx d theta is going to go inside the integral and d theta is going to stay on the outside. Now we are going to switch A and B into alpha and beta because these become angles now because you have d theta at the end, right? It's gonna stay A and B if you have dx or dt, but if you have d theta, they change to alpha and beta inputs because those are angles. Inside, we have our dx d theta squared plus dy dx squared dx d theta squared, dx is die over here, and we have this d theta at the end, which is this d theta. Oh, we didn't have to do all of this over here. We didn't have to do the division, because this is all we need, because that's what we have, and we just plug those in. So L is integral alpha beta, and you have your dx d theta squared plus dy d theta squared d theta. I'm going to put, let's go with orange stars over here, and I'm going to put orange stars over here and say plug in, and gonna point the arrow down. You will take these two expressions, you will plug them here, you will square them, and after, so I'll just go like this, insert work here, which is algebra. You will get to alpha beta square root of f of theta plus f prime of theta d theta, which is the formula you want for polar form. Length of curves. It's just, you have to plug in, you have to square, you have to cancel a whole bunch of terms, and it will simplify to this. It's 3 lines there, each one is like a mile long, so you can practice that if you want to. It will simplify to the formula you see on the bottom. And where are my squares on the bottom? This is how terrible I am. I don't know why you keep up with me over here. We should just all go home. Squares. And let's do some problems. Obviously, we're going to do the circle first, because circle is awesome. But maybe we can do something else as well, so it's not just the basic one. I just need to get some problems because this formula is listed on page 835. And we can calculate the curve. Well, they do a really cool curve in a book, which you should look at, which is a spiral. Spiral, you know what the spiral is, right? It goes like that. Mathematical formula for that in polar coordinates is a joke. R equals theta. Just if you write R equals theta in polar coordinates, it results in the spiral like that. you can calculate the length of the spiral by plugging in stuff into the formula. So this is done in a book. I don't want to do the whole thing because you can read it there. So spiral is r equals theta, or you can call it f of theta equals theta. And your theta, let's say, is between 0 and 2 pi for the 1 revolution of a spiral. So if you have that, your length of curve is 0 to 2 pi, because you want theta to be 0 to 2 pi for 1 revolution of a spiral. If you have 2 revolutions of a spiral, go to 4 pi. 6 revolutions, go all the way to 12 pi. Or half of a revolution of a spiral, 0 to pi. So 0 to whatever pi you pick is going to be how much of a spiral you want. And now we have inside theta squared plus the derivative squared. Derivative of theta in respect to theta is 1, so you're getting 1 squared, and then you have d theta. So there you have it. You just need to integrate integral 1 to 2 pi square root of theta squared plus 1 d theta. This one?
Oh, never mind. I was asking about the equal one for the 1 there.
Yeah, I just switched it. Because I messed up. So, how do we integrate this? Yes. Trig sub. Should we do this Calc2 thing here, or just go for the... You love trig sub? Shall we do it? All right. You love trig sub. I know you destroyed that exam last time, so it's good. All right, let's do some trig sub because we can have some. Well, so far, pretty much everything was Calc2 fun. I mean, parametric equations learned in Calc2. We just applied it to another formula that we learned in Calc2. It's like Calc2 so far. So let's do trig sub. This is Calc2. Section 7.4, trigonometric substitution. And I don't like the idea of memorizing formulas. The way the trig sub is taught, for whatever reason that I don't understand, is you have 3 situations. You memorize 3 setup formulas, and then you grind through calculations, and then good luck in presenting the answer. I don't like that. There is a universal method which is not in any of the textbooks, and why? It beats me. There's a universal method that solves all of the trig sub problems the same way. And that is, you set up a triangle. You put the angle theta, and over here you have a Pythagorean theorem, which means that you can assign sides. Because if you have a plus under a radical, that means that the 2 values under the radical are legs. If you have a minus under the radical, that means that the first entry would be hypotenuse. That's something that you should know from the middle school. So, since I have a plus under the radical, that means that both of these entries are legs, and I just put theta and 1 on legs, making this theta squared plus 1 on the hypotenuse. All you need to do now is to write basic trigonometric formulas with values that are always involving a side that is a number. So now I have tangent theta to be given as theta over 1, from where theta is Oh. The problem is already in thetas, so I can't use theta as my angle. So let's use different Greek letter. What should we use? Let's use phi, because we can. So tangent phi, and then we have that phi is equal to tangent theta, and then d phi is going to be, what's the derivative of tangent? Thank you very much. Secant squared theta d theta. Yeah, I'm just anyway. So from here, theta is equal to tangent phi. Theta is equal to tangent phi, because theta over 1 is 1. Because I switched the variable and I switched the wrong variable. So the new angle for trig sub is going to be phi. So when you're writing a trig function, it's opposite over adjacent, so theta over 1. Theta over 1 is just theta, so theta equals tangent phi. So d theta is equal to secant squared phi d phi. There we go, much better. When we write the square root over here is going to be cosine phi, which is the square root divided by, 1 divided by square root. So from here, when we flip the square root and put the square root up, we have 1 over cosine phi, which is secant phi. And we have our substitutions. So my integral used to be square root of phi squared plus 1 d, theta squared plus 1 d theta. Now we replace all of them. The square root is secant phi, and d theta is the secant squared phi d phi. And we have integral of secant cubed phi d phi. This problem couldn't work out any worse than it just did. Secant cubed is one of the worst integrals that you can encounter in your trig, integral 7.3. You have to solve this using, does anyone know? Integration by parts. You have to use integration by parts to solve secant cubed, and it's going to be more work. So the way to solve this is to go and say secant phi times secant squared phi d phi. Now you use your by parts. You have your u and your dv, and then you will have du and v. What is that you can integrate here? Where you can integrate secant squared. Integral of secant squared is tangent, because derivative of tangent is secant squared, then integral of secant squared has to be tangent squared. So dv is secant squared phi d phi, leaving secant phi to be u. Well, the derivative of secant phi is secant tangent. So secant phi tangent phi d phi, and the integral of secant squared is tangent phi. And now we put our arrow for integration by parts to get secant phi tangent phi minus the integral of secant phi tangent phi d phi. Now what's the integral of secant tangent? Secant, very good. So this is secant phi tangent phi minus secant phi, and we are not going to say plus c because we had limits. So now we have to convert this back into thetas, which is easy because we have a triangle. If you remember, our triangle looked like this. This was theta, this was 1, and this was theta squared plus 1. See, you don't have that triangle if you're memorizing formulas. So going back from phi into your original variable is a living nightmare. You have to do much more algebra to do that conversion. Now, I just read these things off of the chart. I know that the secant, we have it before, is just a square root. So secant is a square root of theta squared plus 1. Tangent was just theta minus another square root of theta squared plus 1. And we are computing from 0 to 2 pi. To quickly compute this, I have a square root of theta squared plus 1 as a common factor multiplied by theta minus 1 from 0 to 2 pi. So, square root of 4 pi squared plus 1 times 2 pi minus 1. That's when I plug in 2 pi. Minus, then I plug in 0, which is going to be square root of 1 times negative 1. This is square root of 4 pi squared plus 1 times 2 pi minus 1. And finally, negative and negative gives me plus, so plus 1 at the end. This is exact. If you like the decimals, go ahead and get the decimal. Make sure you have the 12-digit precision because it's very important. And yeah, that was a little bit of mathematical gymnastics here. It's all Calc 2. Yes?
Going back to parts, you did UV minus equal VDU, correct?
Yes.
Wouldn't it be tan phi times secant phi tan phi? So wouldn't it be secant phi tan squared phi? Because there's two tans. Unless I copy it.
Yeah, I'm going to go and shoot myself right now. Yeah, we have to do everything from scratch now. Why did no one tell me it's tangent squared? Out. Forever. There's a square right here, which means all of this is wrong. And I'm just going to put this symbol right here. And I'm going to color it for you. What does this mean? Just do it. Very good. So when you go home, you will weep of how terrible I am, and then you will fix this. And good thing you're not taking Calc 2 with me. So now all of my Calc 2 students are smiling. Yeah. I'm just gonna go and do circle now because that's easy. Fix this. And yeah, fix this. So you have a tangent square over there, and then you have to do more work. You will be using yeah, you have to do it again because secant tangent integral is secant, and then yeah, it's nothing like Calc2 fresh in the morning. A dose of trig substitution with a double integration by parts inside. So yeah, maybe we should put like 6 of these on a test. No? Alright, fine. You win because I really don't want to grade it. Circle, so we can all just be done with this, right? Circle in polar coordinates has formula as r equal to 6. It's the cheapest possible formula you can have in polar coordinates, which is why we use polar coordinates for circles. Compare that to x squared plus y squared equals 36 in xy coordinates, right? Much worse. To find the length of the curve or circumference, well, first of all, we know we have to get 12 pi, right? We are going to do the integral 0 to 2 pi because you want the entire circle, square root of 6 squared plus 0 squared, because the derivative of 6 is 0, and you have to square it. And then you have d theta. So what you're integrating is integral 6 d theta from 0 to 2 pi, and you get your 12 pi answer. You see how quickly this goes, right? That's why we want to use polar coordinates when we have circles and pardoids and these things, because the formulas are easy to deal with. And if you run into squares, rectangles, triangles, and things like that, you will use Cartesian x and y because that's what they're good for. But you always use the right tool. That's the important thing. Please don't smack nails with a remote control into the wall. I've seen it done before. It's very similar. No. Not because I don't want to do it, because I don't want to do it. And you should know that stuff because it's how to do. But so I'm going to take a circle on the board. I'm going to forward, I'm going to 791. No, 793, advanced applying 2 is where you do that integral. So, yeah, it's a course number, yeah, your calculus is 251. 793. The note is my note. You get whatever possible relaxing, exercise something to write it down. Before you study it, do your homework, get 3 problems, they're due next week. If you solve one of them, pretty much A. Go to exam, you get a test, you look at it, in 15 seconds you realize you don't know any of it, right? You will go.
But you solved that one, so it's an A.
So you write the relevant stuff. I believe that this problem needs to be solved by including this, this, and this, and this type. That's good enough. Yeah. Why won't you teach math? About 30 years of math behind it. So you skip one step, you fall in trouble.
Who teaches that? The inventor of the math?
Dr. Gregory Crixon. Yeah, he was about 60 something. He comes in. First he says, "Today my hand will not leave my sleeve." Whatever that meant, he knew it's going to be Eleanor in whatever he writes. He gave us sperm rule transformation. It took him 45 minutes to develop this thing and 3 pages of notes with him skipping steps. And yeah, and then we go to our offices, right? And you redo the whole proof in 3 hours, filling in blanks, right? And he said it's worth to see this at least once in your life. What do you draw as a conclusion from that? Not on the test, right? Yes, we probably do on the test. Derives the royal transformation. 3-page proof. Alright? It took us 3.5 hours to untangle. Once we ended the class, we went to the office. So yeah. Divide that by 3 for your undergraduate calculus 5. Do you have any math majors? Yeah, it's time to put now, apparently, it's all the one. Because it's much easier to do this in like 10 minutes. Charge 300 bucks a week. Right? So, to be a full-time professor at NGIT on a 10-year track, you have to have 2 postdoctoral degrees. You know what that is? That's a doctoral degree, which is 48 credits on level 700 plus courses, and then dissertation for 2 years. The postdoctoral degree is just dissertation research, which you have to do in a year. So technically it's like PhD, right?
You get that through
Yeah, 2 postdoctoral, postdoctoral degree, yeah. So that's like 3 dissertations, 3 publications. You earn as actual quantity. You don't want to lag behind the man, right? You can do this. Yeah. I will never be able to purchase a 1.5 million dollar. But my friend who has 5 certificates takes his family $10,000 for a weekend in San. I go to business. Walk around sad. Okay, we'll see these guys are splashing like 15 people running around. It's like a break because I see this in the same place. Trade versus Calculus 3. You're all going to be poor forever, I'm telling you.
Do we have anything else? No, that's it, right?